Oh, like, and then I looked at it right in there. What is mine?
Balaji, do you mind muting for a couple seconds while I do the intro?
I really appreciate it.
Thank you.
Oh, one. And then I looked at it right in there. What is mine?
Balaji, do you mind muting for a couple seconds while I do the intro?
I really appreciate it.
Okay, so hello and thank you for joining us for the first CGD seminar of the 2022-2023 season. It is my pleasure to introduce V.Balaji, who will be presenting his talk, Are GCMs Obsolete? So Balaji holds a master's in physics from the Indian Institute of Technology in Kanpur and a PhD in physics from the Ohio State University, excuse me. He spent 25 years at Princeton and was head of the Modeling Systems Division at NOAA's Geophysical Fluid Dynamics Laboratory from 2003 to 2021. He contributed to a national strategy for advancing climate modeling and the paper, The Art and Science of Climate Model Tuning. Some of his recent papers include the Flexible Modeling System, where he introduces the concept of the distributed development model to characterize development of model code in contemporary practice, CPMIP, measurements of real computational performance of Earth system models in CMIP6, which is focused on presenting a new framework for measuring actual attained performance of ESMs on different platforms to inform performance engineering, and also Climbing Down Charney's Ladder, Machine Learning, and the Post-Dennard Era of Computational Climate Science. He received President Macron's Make Our Planet Great Again Award in 2017, and as a result, currently holds an appointment at the Institut Pierre-Simon Laplace in Sorbonne. His work on the application of computational technology in climate research and modeling influenced the genesis of the Schmidt Futures Virtual Earth System Research Institute, VESRI. And in June 2022, so a couple months ago, he actually joined Schmidt Futures as a distinguished fellow, where he will work with their talent venture team and science teams on programs in climate and computational science, and continue his efforts to broaden access to climate science tools and technologies in underserved communities and the developing world. So thank you, Balaji, for joining us today. And I will stop sharing my screen and invite you to share yours when you're ready.
Yeah, thank you, Monica, for a great introduction. Thank you so much. Very generous. I'm going to try to share now. Always an adventure. I hope you can see my whole screen.
That looks fantastic. Thank you.
Okay, so there's no blocks, there's no black blots or anything like that. So anyway, thank you very much, Monica. I hope you can see this. So it's a real honor for me. I've been visiting NCAR on and off over the years, and while I can't see you, I expect I know a number of people in the audience. And as Monica says, I embarked on a new adventure a couple of months ago working at Schmidt Futures. But I'll be talking not about my new work, but about the work that's been going on in the stuff I've been thinking about. Some of the papers that Monica mentioned about the computational performance, the cost of running big climate models, the push towards high resolution, and what kinds of science problems still remain. So I'll talk about why this may seem like a provocative question and might seem a bit of a straw man, but I assure you there are papers in the literature right now which are trying to say that the way we've been building GCMs for the last few decades, we should put an end to that and try something else. And we'll talk about that set of arguments, and let's take a look at some of them. So what is a GCM? So I'll talk about what the structure of the GCM, starting with the work of Sukuro Manabe, who was one of the pioneers of modeling at the lab which I worked in for the last 25 years. And he got a Nobel Prize in Physics last year in 2021 to honor the work that the pioneering work he started doing there starting in the early 60s. We'll talk about computing technology, which as I'm fond of saying, computers for the last decade or so have been getting bigger, but not faster. And that's the Climbing Down Charney's Ladder paper that Monica referred to. We'll talk about the increased use of emulators, which I've got to admit that in the latest AR6, the extent to which emulators are used was a surprise to me when I found out about it about a year ago. And then I'll conclude by talking about what I see as the role of GCMs in the future. So let's start with Manabe's work. So the first paper, one of the first pioneering papers that was cited for the Nobel Prize was this one, which is a 1D model of what's called radiative convective equilibrium. So this is the vertical structure of temperature in the atmosphere as a function of height and temperature. And radiative convective equilibrium is that, so basically radiation is kind of creating a stratified atmosphere. So it cools aloft and the fluid is heated from below by sunlight hitting the surface. And once the stratification reaches some level, you'll start convecting. So in the end, these two come into equilibrium. So this is what in this paper they call the asymptotic state of an initial value problem. And they did these wonderful experiments, trying to constrain the problem in various ways using absolute humidity, relative humidity, and so on. And at the end, the conclusion of the experiment is that you can vary the amount of CO2 in the atmosphere in order to vary the radiative cooling aspect to strengthen it or weaken it. And when they tried three different values, 150, 300, and 450 ppm, you see very clearly that the temperature cools in the stratosphere and it warms near the surface. So this is the first indication that this could happen, but this is just a 1D problem, right? So what do you do next? So then Manabe and Kirk Bryan, who was one of the pioneers of ocean modeling, built this first couple model in 1969, which is recognized by Nature as a milestone in scientific computing. And as you can see, it's a very idealized view of the Earth. The poles have been cut off because of various numerical reasons I won't go into. But it's a beautiful, for me, it's a beautiful image. It's like a totem, which is like one of the founding figures of our field, of our entire field of climate modeling, goes back to this one figure, if you ask me. And they tried, there are various tricks in order to make this thing work, which I won't go into, but this is a very idealized model. But in the end, you can go towards now asking, the temperature is not just redistributed vertically, but it can also be moved horizontally by the general circulation. So now we get into the models of the general circulation. And they did the same thing in Manabe and Weatherald, which is another landmark paper from 1975, where they're looking at the equilibrium response to doubling CO2. The dots are some measurements. So this is just temperature. The surface is a function of the 1,000 millibars as a function of latitude. And you can see when you double CO2, the temperature warms pretty much everywhere. So this is it's a confirmation of the idea that if you add CO2, you're going to warm the planet. And they did various things which you're quite familiar with. So they said, okay, is this a problem? Is this an initial value thing? Or if you vary the initial conditions, what would happen? So now you're seeing that they've started with two different initial conditions, which they're calling approach from above and approach from below. So you start above the equilibrium temperature or below the equilibrium temperature, but you end up in the same asymptotic state. So that means that the system has an attractor. In this case, they ran the model for around a couple of years, 700 days or so, and they let it get to a statistic. It's not an absolute equilibrium, by the way. As we know, there's natural variability, so there's going to be some fluctuations about the mean state. But they do get to something that looks like an equilibrium, and they average over the last bit. And this is around 2 years in this model. Nowadays, of course, the period of what we call the spin-up of a model can be measured in centuries, if not millennia. So this is what, from the time of Manabe and Weatherald, Manabe and Bryan to today, this is what we call a GCM. So you discretize the sphere. Here we are showing a lat long grid, but there are other discretizations like the cube sphere. Inside the column, because the depth of the fluid is much shorter than the horizontal extent, and the column is very tightly coupled. So there's the column is a basic abstraction. A lot of what we call physics, which is shown in the box in the bottom left, which are unresolved by the grid that you put on the sphere. They're all represented inside the column. And the resolution of the model as computing power increases keeps increasing, but it does not increase as fast as you might imagine. So for example, the Manabe-Bryan model is around 500 or 1,000 kilometers. And then if you look at the average CMIP6 model, it's around 100 kilometers. So it's grown by a factor of 10. The vertical resolution has also increased from 5 levels in the original model to 50 or 100 or 150 levels today. So it has increased by some factors of 10, the resolution, but not by factors of 1,000,000 or anything like that. And because of that, we work with what are called parameterizations. There are a lot of unresolved processes, and we try to use parameterizations. That means we try to write down equations that represent everything that's going on in unresolved scale. So for example, a cloud field looks pretty complicated. So you have deep and shallow convection, and their brightness varies depending on the amount of water vapor, the condensed water vapor, condensed water they contain. So both radiatively and in terms of their dynamics, they're quite complicated. So we can make some simplifying hypotheses, like one which is the Arakawa and Schubert, which is there are many, many models which are kind of based on this idea of quasi-equilibrium, which is to imagine that there's a number of unresolved clouds of different shapes and sizes, which is we call the cumulus cloud ensemble, and they interact with the large-scale environment to be kind of what they call in quasi-equilibrium. And if you can find different forms, so formally you can express what quasi-equilibrium means, what are the parameters governing it, and that's what a parameterization is. And these kinds of parameterizations we've been trying to build for a long time, and the progress has been very slow in the sense that the uncertainty bounds on measures of climate sensitivity have not decreased appreciably for many decades. So is the idea of the column something that's weak? So can you actually, you can ask the question, we are trying to redistribute heat, moisture, momentum by clouds as a function of a column, the column average variables. And we have had many, many difficulties with it. So you can ask the question, is the question of parameterization ill-posed? Maybe clouds are not parameterizable at all. And why could the reasons be? There are many kinds of clouds, which are called cloud habits here. Deep convection tends to organize either in the form of lines or in the form of cyclones or in the form of mesoscale systems. So if they organize, then they span more than a single column. So you have to have inter-column interactions, which from a column perspective is non-local, which is the word that I've highlighted here. There's a lot of very small scale dynamics, such as entraining updraft, such as cold pools. When you have descending air, they create a density current near the surface, which can act as a convergence boundary for triggering new convection. There's a lot of microphysics of condensed water and then the droplets interacting with each other and freezing and so forth. So the microphysics is itself very complicated. So what tends to happen is that you start with a simple idea like quasi-equilibrium. You try to write a scheme which has a few parameters. And then as you try to fit them to observations, they become what I'm calling Ptolemaic here. So the problem, as we know, if you remember your high school physics, the Ptolemy tried to build a geocentric system to understand the observations that he had of the planets, and he found that you could write some circles, but then the circles had circles on them, epicycles they were called, and they soon became extremely complicated and did not make any sense. And they were simplified finally by Copernicus based on Tycho Brahe's observations, where he made the system heliocentric, and then suddenly the scheme fell into place. So right now where we are is that we don't have a simple scheme, and we tend to write very Ptolemaic schemes. They start simple and then they become very complicated. And despite doing all that, there are some systematic biases. So GCMs across the generations have some certain biases which have to do with, for example, shallow clouds in the Atlantic, which are underrepresented. Then you have like functions of the tropical circulation called the convergence zone, which is poorly represented. You have what's called the double ITCZ. So perhaps this idea of parameterizing clouds is itself a false idea. So what can you do instead? So you can build what are cloud resolving or convection resolving models, which have been around for decades. So this is actually, I'm showing, deliberately showing a pretty ancient cloud resolving model from the early 80s. They actually date back to the 70s. So you can see that here you're producing, this is now the clouds are being resolved in this model. I mean, you can see some defects. I mean, they have a certain dome-shaped structure, which you don't really observe in real clouds, but they by and large look like a cloud field. So we've been doing this and then if you look at shallow clouds, which are in the boundary layer, so these ones scale with the depth of the troposphere, which is around 10 kilometers is the depth of this picture. Here you're looking at a depth of a kilometer or so. And here you have shallow boundary layer clouds, and you use what are called larger dissimulation models here with a resolution around 10 meters. And again, this looks like, trade wind cumulus or something. It looks somewhat like a realistic cloud field. So what can you do with that? You can also try to embed these. If you cannot build a global cloud resolving model, you can try to embed these CRMs inside a model which is called the idea is called super parameterization, which is assuming that the cloud dynamics is happening at one scale and the large scale circulation is happening at a different scale. So you're assuming a scale separation. For computational reasons, you have to have highly simplified CRMs here. But they have some advantages because now you can start doing what I'm calling non-local physics. You can have organization, you can retain the memory of their state, so they can, so it's non-local in time as well. It can remember the past state of that column. And you can also potentially communicate with neighboring CRMs, but these tend to be extremely expensive models. But they have some advantages, which I'll talk about later. They're a good target for doing some machine learning stuff. So why is the scale separation a problem? If you look at our observations of the atmosphere, this is a famous paper from 1985, which is showing, so you can think of it, so this is the spectral density, it's the amount of energy density in the motion field, in the kinetic energy field, as a function of wavelength, both on logarithmic scales. If you go to very large scales, around 1,000 kilometers or so, the planetary scale, you have basically, you can think of it as a two-dimensional fluid. You can forget about the depth. And for two-dimensional geophysical turbulence, you typically have a slope of -3, which is observed here. And then you get into three-dimensional turbulence once baroclinicity is brought in, and then you have a -5/3 slope. And that slope essentially continues down the inertial subrange down to molecular scale. So you can see that there is, so if you're thinking about resolutions of 100 kilometers, 10 kilometers, 1 kilometer, all of them fall into this area of the spectrum. So you're going to be truncating anyway. You can go down to a meter scale and you'll still be truncating this part of the spectrum. So because of that, whatever you do, you're definitely going to be truncating this somewhere, and you're going to have some set of unresolved scales purely viewed as a turbulence problem. And then you have ideas such as backscatter, which allow you to try to make an estimate of what's in the unresolved scales and scatter them back onto the resolved scales. So it's energetically consistent for SGS means for subgrid scale physics. In the ocean, it's a little more complicated because the ocean it is simpler than the atmosphere in many ways because we don't have the equivalent of clouds. But on the other hand, the bathymetry or the topography of the surface makes things very complicated. So this is a paper. So you have mesoscale eddies, which is also a form of turbulence, which is very important in the ocean because it can transport momentum for long distances. There are coherent structures that can actually travel across the ocean. And they have a characteristic length scale, which is called the Rossby deformation radius, which you can evaluate, and you can compare it to what the resolution. So this paper is asking the question, what resolution of ocean model do you need in order to resolve the baroclinic deformation radius? That means 2 grid boxes to resolve an eddy. And you find that it varies widely. So for example, in the middle of the tropics, even a 1-degree model resolves mesoscale flow. But if you go towards the poles and near the coast, then you have to get down to very, very fine scales. 1 degree is around 100 kilometers, by the way, and 1/50th is around 2 kilometers. And so you need to get to extremely high resolutions to start resolving the mesoscale in the ocean as well. So the point is to make that, there is no target resolution where you can say all the physics you're interested in has been resolved. And if you try to do this, there is no scale separation, basically. If you're trying to do the kind of coarse graining where you're trying to do averages of a field like this. This is a model run by using the French model NEMO, which has been run at 2-kilometer resolution over the Atlantic, and you can see that there are structures at extremely fine scales. And people have been trying to see if you can use these very high resolution models to learn from, for example, the Bachmann paper, which some of the ocean modelers in the audience will probably know very well. And so the other thing you can do if you do not want to do coarse graining because of the scale separation issue is to just run the whole problem at very high resolution. So this is the diamond experiment, which is running a lot of models in this case, this is the first generation of diamonds, so they're around roughly 3-kilometer resolution. And the point they make is that one of these is a satellite image and the rest of them are models. And by and large, they look kind of similar. So it's hard to tell, at least in terms of an instantaneous snapshot, you may not be able to tell which one is the satellite data. But of course, if you start applying more tests, you'll start finding some flaws in the models. But you can say that you have started to resolve something important. So you're no longer parameterizing cloud. So you've made a pretty significant advance in that respect. On the other hand, the point I made is that from the time of Manabe, the resolution has not evolved as much as one would like. This is a paper from Schneider et al., which is showing, the blue line is showing what logarithmic doubling of computer power, what resolution it will get you to. And in theory, you could be on this scale of doubling, and you would get in the year 2020 to around 100-meter resolution. Actual models are falling well short of that. That's another thing. The models also are complex in various ways, which do not. Adding computer power also means that you make the models more complex in terms of the physics you're trying to represent. So it's not just resolution. But the point is, even if you went along with resolution, in order to resolve shallow clouds, for example, which require, as I mentioned, 10-meter resolution, you're not going to get there for the foreseeable future of a number of decades. In fact, I would argue that you're never going to get there at all, because as for reasons I'll show below. The second thing we have to remember is that we have to run these models many, many times. It's not a question of just running a single realization. And the reason for that is summarized in this figure by Hawkins and Sutton, which is much reproduced. There are lots of new papers based on CMIP6, which are trying to use this kind of approach to understand uncertainty in the CMIP ensemble. So this chaotic uncertainty, which is internal variability of the system, which is shown in orange here. And then there is what we call structural uncertainty, which is the deficiencies of the physics. And as a function of lead time, going forward many decades. And then the third thing, the green bar, is the scenario uncertainty, which are forcings which in our models are external to the system, which is CO2 emissions emitted by human and natural systems that are exposed to climate change. So this uncertainty going over many decades is the largest. The chaotic uncertainty tries to die off over time. The force signal becomes stronger. For very short times, the chaotic uncertainty, which is dependent on initial conditions, is as important as the other kinds of uncertainty. But in order to sample this whole space of uncertainty, to do climate change over the period of even 1 century, so you need to be able to run hundreds of simulations. So that's one thing to keep in mind. So it's not enough to be able to run 1 or 2 simulations, because you're trying to do all these counterfactuals with different levels of forcing and all that. So we have a baseline requirement for what I'm calling a GCM, a climate model that's capable of understanding the forced response to external forcings. So 100 simulations of 100 years each in a reasonable amount of time. So that's kind of the requirement of a GCM. And the observational record itself is pretty short relative to this. So that's also something to keep in mind. So this is a paper I'm going to just refer to very quickly, which is both in the CMIP, this is the CMIP5 ensemble, both in the CMIP5 ensemble and in the CESM large ensemble. And you're seeing essentially this idea that the Hadley cell circulation, which is the strength of the tropical circulation, measure of the strength of the tropical circulation, appears to be weakening over the next century. On the other hand, the green lines are taken from various reanalysis data sets, which have been forced by observations, which are using data assimilation. You're bringing them in line with observations of the last few decades, starting 1980 or so. All those seem to show that there is a relatively, over the last few decades at least, it seems like the Hadley cell circulation is increasing in strength rather than decreasing. What is fascinating about this paper is that they argue that because of using data assimilation and all that, there are certain conservation laws which are getting violated. So they're arguing that it's quite possible that the models, so-called models, are correct, and the so-called observations, which are actually also based on models. Let's not forget that many things we call data sets are based on reanalysis, which have models behind them. They're actually showing an increase, and perhaps the reanalysis are incorrect in this regard. So we have to be careful. The word overfitting we'll return to, because I'm going to start talking about machine learning. So what do you learn from is a question that we have to be concerned about. Very quickly on the computational technology, I made this point already. So, which is that for the last decade or so, we've been relying for the last many decades on this idea of Moore's law, which is that the density of transistors keeps increasing exponentially with time. So this is showing on a log scale on the y-axis. So roughly doubling every 18 months is the number of transistors. On the other hand, the green curve, which is the important one here, is the frequency, which is the speed of a single mathematical operation. That has not changed appreciably for a decade. So because of that, what it means is that you can run what I call weak scaling problems. That means you can run a bigger problem in the same time as you did a decade ago. But the strong scaling, which is the same problem, trying to solve it faster in the same time, does not work. So it's mostly all of the technology changes that we have been seeing over the last decade are applicable to weak scaling. So that means that people are trying to solve bigger problems, which means they're trying to add resolution rather than trying to solve the same problem without adding resolution in a shorter time. And what happens if you reach an exaflop? This is a paper by Neumann et al. From a couple of years ago, which is talking about at what level of flops, petaflops, exaflops, and so forth. The phenomenon, this is atmospheric centric, but you can see similar figures for the ocean. If you get down to 1 kilometer resolution, deep convection gets resolved. Shallow convection still does not. Using the ICON model, these numbers have improved a little bit, by the way, since this paper was written. But essentially, using the German model, a 1 kilometer model will run at around 0.06 simulated years per day. So you need quite a bit of improvement in software or something in order to get to 1 simulated years per day. So, but the idea is that since you're not doing parameterizations, you have a vastly reduced uncertainty at 1 kilometer. So the whole idea of digital twins, the Destiny project in Europe, the Next GEMS project, all that are based on this idea. Again, I want to remind people that if you want to participate in something like a CMIP, you need to be able to run at least 1,000 years. As I said, I think in order to sample uncertainty fully, you need to be able to run many simulations that are 100 years long. And we have not yet even started talking about the ocean. The ocean has memory that's very important for the climate system as a whole. So what can we do with these modern computers? So here's an example. This is just a simple illustration of why deep learning is a great application of the new technologies. So let's assume that you have some data, which is an input vector and an output vector shown in blue and red. So here, this is just a cartoon. So you have 5 input points and 4 output points. So if you're doing a simple linear regression, you would have about 20 possible weights to compute in order to find a relationship between them. So for 5 and 4, for 9 data points, you have about 20 operations. Now imagine if you put in a hidden layer in the middle that's called the neural layer, and now you have 7 points in there. So now you see the number of black lines. It's going 5 times 7 and then 7 times 4. So they multiply them and you'll see the density of arithmetic is vastly higher. And if you go to deep learning where you have multiple layers of neurons, it becomes extremely dense for the same amount of input data, same 5 and 4. The amount of arithmetic you do is vastly increased. And you can do nonlinear fits between these two, which are very accurate fits between the input and the output. So because of this, these new machines, they've gone from CPUs to GPUs, the graphical processing units, to now what are called TPUs, tensor processing units. They're all fabulous at doing this arithmetic, which is why I think we should be thinking very hard about how can we apply this, how can we use this technology for our models. So I think this is the big reason to really take machine learning seriously. And they've done wonderful jobs at various kinds of problems. For stationary problems, which means that the boundary conditions do not change, people have shown, for example, Patek et al., and there have been many papers since then out of the same group, essentially showing that they've taken an equation called the Kurotomo-Sivashinsky equation. It's a canonical classical ODE system. And you can learn. So this is the time series from the original data you're trained on, and a neural network of a kind, which is called a recurrent neural network or a reservoir computing echo state network. It can be trained on it and reproduce it very well. So now you're showing the difference between the original data and the learned one by the machine learning, by the learned network, and measured in a unit which is called Lyapunov times, which I'm not going to go into the details. It's for people in nonlinear dynamics field are familiar with it. It's the reproduction is pretty exact for many Lyapunov times, which means that it's an extremely accurate reproduction of a chaotic time series. But the problem is stationary. That is, there's no parameters in the KS equation have not been changed. If you do change them, that means an external boundary condition is changing, then you have what's called a non-stationary problem, There, the learning problem is far more difficult because you have to be sure you have enough data to sample many possible values of the external parameters. And there are some papers such as O'Gorman and Dwyer, I'm not probably not going to show the details, which show in the climate context, as the climate is warming, if your training data is based on historical data which has not seen some of the warm states of the climate, then the learning from those states is probably inadequate. So one thing you can do, of course, is instead of using observational data, you can use models which I'm calling up the ladder, which is like, for example, running a CRM, a cloud resolving model, and then using that as training data for building a GCM parameterization. So what is the difference? So is the CRM actually reducing uncertainty? So this is a paper from an experiment called RCEMIP, a beautiful experiment that was designed by Alison Wing with the help of many people, including probably some in the audience. Masaki Sato from Japan was one of the key developers of the experiment. It's running the original Manabe radiative convective equilibrium experiment, but the experiments have been designed so that both CRMs and GCMs can participate in them. And the question you ask is, are the CRMs in any appreciable way better than the GCMs for these sets of experiments at least? And these are idealized experiments, so we're not comparing them against real data. We're just seeing whether the spread is reduced. And by and large, you see that the spread is not reduced in these idealized experiments. In a recent paper, which has the same title as the seminar, which has just in the last 1 week or 2 weeks been accepted at PNAS, we did the same comparison of seeing whether comparing CMIP versus diamond, whether the uncertainty is reduced. So this is comparing, looking at the upwelling long wave top of atmosphere radiation as a function of precipitable water. So the blacks are some of the CMIP data and the reds are some of the diamond data. And you'd see that in some cases it is reduced. If for other things where now you're measuring albedo as a function of cloud fraction, you're seeing no appreciable reduction by going to an RCE, going to a CRM instead of a parameterized convection model. So there is what we call structural uncertainty, which is just spread between different, it's not as though we know the physics, therefore every CRM is going to do the same thing. That's not how it works. There is still a difference. And if you go to LES models of the boundary layer, so this is another experiment from the group in Caltech, which has taken forcing data from what are called CF sites. If you're familiar with the CF MIP experiment, it's looking at the cloud forcing at particular locations around the world. So it picked 23 canonical locations, which are different, which are spanning different cloud regimes and so forth. So here, what you're seeing is that they've taken 2 different GCMs, and if you compare across them, looking at liquid water path difference between the 2 models, they can be quite big. So there's big differences between 2 different models in the CMIP. They're just 2 picked at random. There's nothing good or bad about those models in particular. There's quite a big difference between them. You use the same data from the GCM and you force an LES model with it, then you get a vastly reduced uncertainty. So you can say that the LES does reduce, in this case, the GCM structural uncertainty, but there are so many papers that showing that the details of the LES in terms of the numerics and the turbulence closures that they use also make some differences. The point is that structural uncertainty will not actually disappear just because you keep adding resolution. You will still have some closure that you're using, which will have some tunable parameters, and and there are various ways of representing those scales, and there will be differences between them. So let's move to the topic of emulators now. So, and starting with the idea of what do we mean by emulators? It's that you take physics from, you take the output from some model, which is high resolution, let's say it's expensive, and you try to learn from it using machine learning. So how do you do that? You have to write some sort of a cost function, which is saying I'm minimizing some metric of distance between the original data and what the neural network is doing. There are problems which have to do with the fact that the models that we have are not really scale aware. We like them to be, we're not quite there yet. So they do not converge cleanly with resolution. Simply making computation, as I hope I've convinced you, is not going to make the problem go away. There are many beautiful new observations, both from space and from floats in the ocean like Argo. So why can we not use ML, which the computers are really good at, in order to learn from high resolution data or models in order to calibrate other kinds of models. So what does calibration mean? It's also called tuning. You write down, as I said, some metric of distance. So you have n different metrics, let's say different observations of different physical variables. You have some measure of distance from observations, and you have a parameterization which has some tunable parameters. And you try to vary the parameters in order to minimize some cost function where you apply some weights to the different observations. So the weights and all that become kind of tricky. How do you pick the weights? So some of it becomes part of the lab's culture. Different labs value different things and they weight them differently. For example, if you went to an Indian center, they would probably assign a lot of weight to getting the Indian monsoon correct. Other labs may not. Two things you must keep in mind once we get into the ML world, that this overlap between the metrics you use for tuning and the metrics you use for evaluation, this is called data bleeding. So it's recognized as a problem in machine learning. There's a new paper showing that many ML papers are not reproducible because they've allowed the validation data to actually bleed into the tuning, the training of the model itself. So you have to keep them quite separate. And then the problem I mentioned of overfitting, the recent history, the last 50 years, 60 years, where we have good data about the current Earth system, is one realization, and it might have a lot of, the system is chaotic, so we should not take every wiggle seriously and try to learn it. That's what's called overfitting. A couple of examples of tuning. So this is from a GFTL model. So you have choice of metrics. So I'm going to rush through some of these slides very quickly. I'm sorry, I'm happy to answer questions, but you had the choice of tuning either the global cloud field or simply removing biases in some local areas where the biases are strong. And you can do that. So the left half of the figure shows that you can actually tune to reduce local biases in cloud fields where they're known to be strong. But that means that the overall cloud bias becomes larger. So you have to make this is what I mean by culture. So you have in tuning, the paper we wrote is called the art and science, because some of it is an art. It depends on what the scientists choose to value. So this is a set of papers describing how this is done. And some of the key things is that tuning each component separately and then trying to couple them has a lot of difficulties. So there's some quotes from here showing that we have to coordinate across the component models. And there are some biases that do not show up in uncoupled systems and then show up in coupled systems. It's quite expensive, this whole tuning process, the way it's done today. In the GFTL series of models, we did about 50,000 years of coupled model tuning in order to deliver 10,000 years of CMIP runs. Then there's a question about should we tune to get the 20th century? I'll leave that for the discussion, and because this is the overlap between tuning and evaluation metrics. You cannot tune for the 20th century and then claim success because you got the 20th century correct. So what can you do with ML? You want to explore the parameter space using emulators so that you're not running the full GCM each time you want to evaluate a new set of parameters. And so there's still the issues of weights and cost function. And then you have to have this two-stage process where you do each component separately, which I'm calling process fidelity, and then you apply the global constraints. So, and then there are some other questions. Do the observations sample the space sufficiently? If you're using 50, 60 years of the recent observational period, that's clearly not enough for the climate system, which has low frequency variability. If you're using LES and CRM models for training, you have to know about their uncertainties as well. And then you have the issue of compensating errors, which I'll get to in a second. So one project I've been working with in France is called HiTune, which is using one method of, it's kind of an important point here. They have a metric which is called implausibility. Lambda are the parameters you're varying. It's the parameters in your parameterizations that you're trying to find good values for. So you have a measure of distance. You use emulators, as I'll show in the next slide, to evaluate, to get this metric, the implausibility metric, under some tolerance that you've chosen. And that space that's left is called the NROI space, not ruled out yet. That is, the physics that you know is not ruling out this value of parameters. And you can use different metrics in different waves. So they call it iterative refocusing. So you have, and you end up with, at the end of n such waves, an NROI, which is a small area volume of parameter space, which all the values within those are equally valid. So you're not actually optimizing, as you see, you're just eliminating implausible values, and you're left with many sets of parameters, or a few, which are all equally likely to fit the data. And the way they've done it in this paper is they use an LES as a reference, and then they're using a single column model with a parameterization in it, and they're trying to tune it, and then they build some emulators and so forth. So I'm not going to go into the details. So the emulators are tuned to fit the parameters of the single column model to what the LES is telling them is the truth. The Gaussian process I'm going to step aside. So what you're left with is a small area of the space, which is the black dot is the truth you're trying to, because you're here, you know the answer. So this is what you're trying to tune towards. And you're left with a small parameter space, as I said, which is not ruled out yet. And sometimes that space can actually go to zero. That means it's what it's telling you is that no values of parameters in your parameterization can possibly fit the data. So that's what we call structural error. So you can diagnose, you may not be able to do anything about it. If you find structural error, it means you have to rewrite the equations of your model. So how do you do that? So this is a different way, which is, again, I've been referring to the CLIMA project from Caltech. So they use a method called Calibrate, Emulate, Sample, which is kind of similar in approach. So you first calibrate using an expensive forward model, and then you use emulators in order to do an uncertainty span of the space, and I'm giving you a set of references to go into that in detail. And then I'm going to skip ahead to make one last point, which is you have this idea of, if you have two sets of physics, when you go to the second stage of the process and you're trying to calibrate the couple system, we often have the problem that we all know, people have been building GCMs for years, that you can certainly end up with a system of compensating errors where there's two sets of errors and two different components that cancel each other out to give the right answer for the wrong reasons. So we're using the Lorentz 96 system, which is a two-scale system. So you can usually, they say that this is the resolved scale is called the X, which is the slow modes, and then the Y's are the fast physics, which is you're trying to emulate to the parameterization. In this paper, we're treating this as the couple model. So in a paper that we've written on this, which I'll be referring to, so you're treating X as the slow, so it's the ocean, and Y is the fast, it's the fast physics, it's the atmosphere. So you're trying to now tune a couple system. It has four free parameters, F, H, log C, and B. So you run it once, you find the truth run, and then you have certain metrics, some of which are, the X's are based on the ocean state alone. Some are Y bars, which are based on the atmospheric state alone, coarse-grained. And then there are some which refer to the couple state, like X, Y bar. So this is a paper we have submitted to James. It's in review right now. And we're trying to see what can happen here. And you can indeed tune the system, what we can show, but we can also, if you tune just the atmosphere and the ocean, that is just the X's and Y's separately, it is showing, for example, you can get into these states where there's two possible solutions. You can maybe see it a little clearer here. So there's two lobes to this. So these are you can at least diagnose, you may not be able to do anything, okay, you can see it here. So you can diagnose that there's two possible values of two parameters, which can both give you the right answer. And when you see that, that means you have to use some other means of picking one over the other. So here, okay, here you see it in this case a little clearly, where you're trying to tune F and B together at the same time. And there's two possible values of F and B that give you the right answer, and you have to pick one over the other. And that's where some of the insight into physics and all, that's where the expertise comes in. That's where the art of tuning also comes in. So this is the way you can mix expert knowledge along with what machine learning is teaching you. Another one, which I'm not going to talk about in great detail, but it's exciting new work, which is that you can also actually try to learn, you can use arithmetic of symbols to actually come up with formal expressions rather than just doing machine learning fits. You actually come up with an equation for the terms that you're trying to discover. And this paper is showing that while, so you're trying to learn the data which is in the cyan, which is on the top, which is the an energy spectrum as a function of time. And if you, with low resolution, you're definitely not simulating the energy that you need, but you can get closer and closer with different methods of neural learning. And one of them actually is finding a set of equations that does an adequate job of fitting the spectrum. So equation discovery is an exciting new field as well that's showing up in machine learning. I mentioned non-locality a few times. This is another thing that's an important thing to realize about machine learning. While the column abstraction is basically trying to do physics based on column average variables, you can, with neural networks, also go towards learning from neighboring columns. You can use data from neighboring columns, and for that matter, you can also data from the past state of your column. So you can go back non-local in time and space, and you can still build neural networks, and you can learn pretty adequately. So this paper, Wang et al., is actually showing a good results from using non-local parameterizations. So again, each of these, I'm just giving you a bibliography of people doing various kinds of approaches to learning. But then finally, I want to get to the problem or the thing that I did not realize about Ipcc Ar6. So Ipcc Ar6 uses GCMs much less than you might realize, at least much less than I realized until I found out about it, which is, for example, they want to do these single forcing experiments, because one of the requirements for the Ar6 is to say how much a particular forcing like CO2 or methane or N2O is contributing to global warming. And it's too expensive to run each of these single forcing experiments. I know that, for example, CESM Lens has done this now, but it's done much after the fact. But I think it's hats off to the team for doing this. But most modeling centers are not doing these single forcing experiments using GCMs. They're just very expensive. So, and then the second problem is that there's a Housefather paper called the hot model problem. There was a large spread in climate sensitivity in the CMIP ensemble. So they constrained them. The Ipcc Ar6 used to constrain them using the fit to the recent historical past in order to constrain the spread. Both of these are done using highly simplified models, which are called reduced complexity models. They have not little or no physics in them, but they're millions of times faster than GCM. So you can do all kinds of experiments with them. And there's a much increased use of RCMs in the Ipcc as opposed to CMIP than I realized. And there's an interesting talk that Ben Sanderson, formerly of NCAR, now at Cicero, gave at WGCM, where he said the role of the ECM is increasingly as a target for robust emulation. So this is sounding similar to the argument I was making earlier, that CRMs and LES models can be used to train parameterizations. So Paleo Climate, again, I'm going to skip. The only point I want to make on Paleo Climate is that I think it's an important constraint on climate. That is, if you're building machine learning-based models, you want some out-of-sample testing, especially if you're training them on the recent history. We know that current generation, or this is a paper from 2011, so the models have got a little better. I know that the CESM in particular has done a good job with some of the Paleo Climate runs. But essentially, this is the PETM problem where we know from data 55 million years ago, there was a rather equable climate, which means the temperatures near the poles were pretty warm as well. And there's a lot of evidence to back that up, but the models don't do a great job. They still have an equator to pole gradient of temperature that's very large. So there's not enough data here for machine learning, obviously, but I think these are Paleo Climate is a good thing of what machine learning calls an out-of-sample test. You train with something else and then you test it on Paleo Climate models. So I think that I'm pointing to the importance of Paleo Climate. So to end, climate is not weather. So there's a difference between stationary problems and non-stationary problems. I think they're going to diverge further. There's a lot of good work coming out. You might have heard about ForecastNet from NVIDIA. So there's a lot of people who are building forecast models going out to a few weeks, which are entirely based on emulation. That is, they're just completely machine learning. There's no physics in them. So Guardian actually asked, are we witnessing the dawn of post-theory science? Maybe we don't need theories anymore. Maybe we just do this. I think that's not going to work for non-stationary problems. I'll say again, computers are getting bigger, not faster. So let's not assume that computing is going to get us out of this problem. All models are tuned. all models are calibrated. Some are over-calibrated, but everything has been calibrated for various means. Machine learning, what it lets you do, in my opinion, is that it lets you use emulators to vastly accelerate the process of tuning. So you should be able to calibrate models, new models for different purposes in weeks, not years. And you'll need that all the time. And then these reduced complexity models that are used for IPCC, if they're completely decoupled from physics, then I think there's some epistemic risk. We cannot really say how these emulators will respond to some climate surprise. We don't really know. I'm pointing to some references to these papers, Charney's ladder and our GCMs obsolete, both of which are, our GCMs obsolete is currently available on archive. Saravanan at Texas A&M, who also used to work at NCAR, has written a nice book called The Climate Demon. I mentioned Ben Sanders' talk already, and we just had a great workshop in Stanford called Modeling Hierarchies, where I saw some of you. And finally, I'm arguing that GCMs are not at the end of the road, but they are the crossroads. We have global cloud resolving models, we have small CRMs, and we need to get to Paleo Climate models, and we need to get to these single forcing runs. And even though the column might look like it's broken, I think machine learning allows us to connect all these models up, and I think GCMs will still remain at the center. Thank you. I'm going to stop there, and I'm going to stop sharing.
Okay, thank you very much for that comprehensive look at climate modeling and intriguing talk. So I would like to open up the floor to see if anybody has any questions, because we do have about 8 minutes left. So if you want to raise your hand if you have a question, or you can also put a question in the chat. I will invite people to do that now. And you can use the raise hand function because I can see if people are doing that. Okay, so Jean-Francois has a question. So yeah, go for it.
V.Balaji, thank you. So super interesting talk, of course. On your last point and the role of machine learning and being kind of the glue between all those, are there at this point significant limitations in what machine learning can do, or is it really just reduced to a data problem of having enough data to train the machine learning?
So I don't think it's a done deal yet. I think it's still an open question, but I think it has a lot of potential, and I think we should be taking it seriously. And that's all I will say. I don't think it's a done deal that machine learning is going to get us out of the computing bottleneck that we are in right now. The advantages that I see are, one is that it can fit lower dimensional representations, so you can do that. And as I said, there are methods that will, at least it cannot give you a solution, but they can diagnose the existence of structural errors. That is, if you've written an equation and the equation actually cannot fit the data, there is a way of diagnosing that. And secondly, if in a coupled system, if you build in compensating errors, which we know that our current generation GCMs probably all have this problem, again, I think there are ways of diagnosing that. So I think machine learning is taking something that is a little bit of a black art, which is calibration, and it's making it formal and it's making it explicit. And I think that's going to be a major step forward, in my opinion.
Thanks.
Okay, thank you. Any more questions? So Julio, do you want to unmute? And then there's also a comment in the chat that I might, yeah, so Brian has raised his hand too. So let's, Brian, since yours is a follow-up, why don't you ask your question quickly, and then Julio, I'll open it up to you.
Sure. So thanks for the talk. This does follow on JF's question. It was more from what I've seen of highly successful machine learning models like AlphaGo or some of the chess playing engines. They cost millions of dollars to train before they even got better. Like you could look at the ELO rating of the chess engine, and after $10 million, it was still really poor. It took until around 25 million before it started to asymptote up. those are simpler problems. So what can we expect in the climate space, given this cost of training?
Yeah, so I think that's a great question, and I agree with you that the cost of training is high, and AlphaGo is actually working on a far simpler problem in terms of dimensionality compared to the climate system, in terms of what the size of the space that it has to sample. And I will go further than you in terms of the dollar cost to also talk about energy cost. I mean, the energy cost or the carbon cost of training is immense. I mean, there's quite a few papers you can find talking about how much AI is actually contributing to global carbon budgets. So yeah, the cost of training can be very high, which is why I think I'm arguing for methods that combine machine learning to formalize the process along with a scientist in the loop. I'm not talking about eliminating it altogether, which is what AlphaGo is doing. So AlphaGo's big advantage in chess over Deep Blue, or whatever it was, the one that beat Kasparov, Deep Blue, I think it was something like that, or Blue Mind, something with the word blue in it anyway, it was IBM. So AlphaGo's big advantage is that it actually learns by playing itself. So it's reinforcement learning is what the method that it's using. It does not go in from having read all the classical books on chess strategy. It makes up its own strategy. So it's completely self-trained, and it's based on really large volumes of data. And we are not talking about that. I mean, first of all, if you extrapolate the volume of data needed from chess to the climate system, it will be, I'm pretty sure it'll be some astronomical number of zeros. So I don't think that's even feasible. So it has to be a combination of scientific insight, expertise, and machine learning. But machine learning, I think, gives you a framework to formalize the process.
Okay, thank you. And Jim did put a quick comment that Go and chess have well understood parameter spaces, whereas the Earth, physics does not. So Julio.
No, thank you, Balaji. I just, it seems from your talk, at least for me, that machine learning can, inform subgrid parameterization and as well as speed the tuning process. But it's not clear to me how, we still have is it unavoidable that we have to run tens of thousands of years to really characterize variability in the couple system, sort of along the lines of a large ensemble, or are there alternatives to, having to just do that?
So in terms of, if we go back to the Hawkins-Sutton diagram, which I hope I don't have to pull up, I hope you've seen various versions of it. Everybody has seen them. So the scenario uncertainty is something, or if you want to do, for example, single forcing run experiments, if you want to explicitly say how much is methane contributing versus CO2, there's no alternative but to run two different runs with different sets of single forcings.
No, well, I'm just talking about for a single forcing scenario, just, fiddling with the initial conditions, you can have vastly different answers in 2000, in 2100.
Correct. So there are other methods are possible. They're mathematically, the people have tried to express them. We have not successfully done anything other than actually running ensembles in order to sample this kind of, that's why I was trying to distinguish. I was trying to get to your point, Julio. So there is a distinction between the initial condition, or what I'm calling chaotic uncertainty, and scenario uncertainty. So the scenario uncertainty, which is external, there's no choice. We have to sample each one. For chaotic uncertainty, are there better ways? In theory, there are. There are a class of methods called Fokker-Planck methods, which essentially allow you to replace each physical variable from, rather than have a deterministic value, you have a distribution of possible values. So it's a PDF. So formally having a PDF with a certain shape function and then trying to go through nonlinear dynamics with that, it quickly becomes intractable. But there may be deterministic methods. So there is a vast literature emerging in probabilistic machine learning, which I think we should again be paying attention to. I'm just kind of learning a little bit about it, but I hope we can get to better methods than what we're using right now, which is actually running out the same physical system with just different initial conditions in order to sample uncertainty. That's one way of doing it, surely, but we must be able to get to more efficient and less energy expensive ways of doing this. I hope we do.
Thanks.
Okay, Balaji, are you okay to take one more question?
Oh, yes.
Okay, Rich, go for it.
Last question. Great talk. From a pragmatic point of view, climate models are used to look at future predictions. A lot of that is extreme events. And I wonder what's this kind of state of thinking of machine learning being trained on present day stationary climates. You mentioned it a little bit. And how do you think they still have a problem in predicting things like, for example, from the UK, we have the most extreme surface temperature, and it was more than X standard deviations away from what it was, versus a prognostic, forward model being able to predict that. Do you feel that neither of those approaches were able to access the phase space of this 3 standard deviation event, or do you think one or the other has an advantage on that?
Yeah, so that's a great question, and I don't think I have a fixed answer for you. So from the machine learning perspective, it's clear that if you're starting to talk about rare events, and for machine learning problems, you can definitely constrain them ahead of time by saying, I do or do not have enough data in order to constrain my system. So if you're given a certain number of neurons, you can say there are well-known heuristics for how much data you need to constrain the problem. So you can certainly say there is none to constrain 3 standard deviation problem. You do not have enough data certainly in observations. Of course, models is a different story. So there's a class of methods that's coming out, which are called rare event methodologies, which allow you to create ensembles where you have a higher rate of incidence of so-called rare events artificially. And then from that, you can backtrack the real PDF because you know the way you transform the system to oversample the rare events. Okay. But they're still theoretical. They're being built on highly simplified models, certainly nothing like a real GCM. But so there are people who are working on such methods. That's all I can say. So there's some good literature if you go look for rare event algorithms, which can lead to that. But the other problem is we probably know from experience that a GCM's performance on mean state evolution tells you nothing about how it does on variability and vice versa. So you can have models that have large biases in the mean state, but they capture variability pretty well. And you have other things that simulate the mean state. The emulators, for example, certainly only simulate mean state. The emulators that are used in Ipcc, they know nothing about variability. To capture variability or regionality, you have to add other methods like pattern scaling. So you can have one or the other. So it's hard to diagnose one from the other. But again, all I'm saying is that I think ML is making us focus our attention to formalize everything we're doing, which we're doing by kind of hand waving for the last few decades.
Thanks.
I have a couple of chat questions. Should I?
Yeah, there's one in the chat that you're welcome to provide a quick response to. So it's Dan Amrine just wondering how an increased machine learning focus should be coupled with increasing data collection for training.
Yeah, so I think I'm kind of would argue for using model output as training data of models up the ladder, as I call them, so up Charney's ladder. And for that, I do think that if people are running high resolution simulations, especially if they're running these 1 kilometer global, so I'm pleased to note that the IFS ran a 1 kilometer global on the Oak Ridge machine, and they made the entire data set available for other people to use. So I think making every expensive run that we do, the data should be public so that it can be used for training. I think it's a tremendous ways to use up all that carbon, run this experiment, and then there's not much data that other people can analyze. So I would say yes to Dan's question, not just increase data collection, but increase data publication.
Okay, great. Thank you. And I think that's a wonderful note to end on. So Balaji, thank you so much for joining us for our first CGD seminar. I think we're just going to close down now. So thank you.
Thanks for the opportunity. Pleased to see a lot of you. Thank you.
Yeah, thank you.